Today we have a really strange problem here on the board. We've got the integral from 0 to infinity sine pi x minus sine ex over x dx. So this one came up as it's kind of similar to some problems I did recently. In another video not too far back, I did a problem that was set up just like this, except instead of sine we had arctan. And I don't think it was pi. Well, I think there was a pi, but it wasn't an e, but we had arctan instead of sine. Now, when we had arctan, that's actually an example of Frullani's integral, but that's different because the key there is when you have arctan, if you have this set up where you have like arctan pi x or whatever, when x is going to infinity, this still exists for arctan because arctan is just going to be pi over 2. And the other check is when x is equal to 0, arctan of 0 is just 0. Notice that doesn't work here with sine. When x is going to infinity for sine on either of these, that limit doesn't exist because sine is just going back and forth from -1 to 1 forever. So we can't ever get this infinity value. The 0 value is fine, but this x value is a problem. So the problem we have here is not quite like this arctan problem I did a couple weeks back. And also not too far back, I did one with cosine. This is different from that as well because with cosine, notice with this one, we could actually just split this in half because I've done videos on something really similar. Like I did sine x over x. So we can actually just break this into two integrals. If you do the same thing with cosine, it doesn't work because the individual integrals don't converge, whereas here with sine, they actually do converge. So what I want to do for this is actually do it that way. We can split this up into two integrals, but really what I'm going to do, I want to use Feynman's trick on this. So I'm going to kind of just generalize each of these. What I can do is I can create some function. We'll use a variable. We'll create a new variable s here. And I want it to just be one of these integrals, right? So we can do, but what I'm going to do is instead of writing this as sine pi x, let's write this as sine ax over x. And see, what you might want to do is you might want to parameterize the a. I think if you do it that way, you end up with all kinds of trouble. What I want to do instead is create something in front here. We'll create an e minus sx. The reason this is going to be nice is you notice when x is 0, this piece right here is just going to be 1. So what we can do is use this f of 0 value later on. And then based on whether if a is pi, it's going to be this one. And if a is equal to e, it's going to be this case right here. So we'll come back to this. But the other nice thing is we have the value. You'll notice when s is going to infinity, then for this f of infinity value, this part here is going to 0. And that's going to cause the whole integral to be 0. So we can use this value later on. That f when s is going to infinity is just going to be 0. Now, one note on this before we continue, there is kind of a really quick way you could kind of just do this from the thumbnail, especially if you saw my other video or if you're familiar with this problem when just like sine x over x. This is going to be really the same steps as the other video when we did sine x over x. But I do want to show how this works. So we're going to go ahead and we're going to differentiate here our f of s function. We're going to differentiate with respect to s. So when we do this, we're going to differentiate inside the integral sign as a partial over here. So we'll write it like this. But for the derivative part, we really just need to worry about this e minus sx part because everything over here, this is going to be a constant with respect to s. So we're just going to rewrite this and leave it over here like this. And then we go ahead and differentiate over here. First, we're going to get back the same thing. We're going to get back e minus sx. But then chain rule on this here is going to pull out, we're going to have a minus x here, and we'll just bring over this other stuff. But then I can cancel x with x here. I can take this minus sign and bring it out front of the integral. And then what we have left, you may recognize this right here, this isn't exactly the right form for a Laplace transform. This thing right here is going to be the same thing as the Laplace transform of the input here, sine ax. And there is a formula for this, so we're just going to use the formula for this thing. But I need to bring this minus sign out front. Then for this, we're going to have in the denominator, this is going to be s squared plus a squared, and we're going to have an a in the numerator. So then this right here, this is going to be our f prime s value, but we need to remember our goal. We're trying to get back to this f of 0 to originally get back to our original problem. So then what I need to do is we need to integrate this with respect to s to go from here back to here. So then to integrate this, we're integrating on both sides now with respect to s. Do it over here as well. Now a is just a constant, so this is actually just set up like exactly for our arctan formula. What's going to happen is, now this like minus a, This part here is just a constant I can bring up front when we integrate this. Then on everything else, we can just use the arctan formula, so it's going to be just 1 over a arctan of S over a. Of course, we have a plus c on the end, and these a's are going to cancel. So out front, we're just going to have a minus 1 here. So let me just bring the plus c in front so we can make it more pretty like that. And now from here, we have our fs, but we don't really want a plus c in here. We don't want a constant. That's where we can use this condition right here in order to evaluate this. So when s goes to infinity, what we're going to have c minus basically arctan at infinity right here. This part's going to be arctan at infinity when we plug in for s. The a is not going to matter. So arctan at infinity is actually going to be just pi over 2. And we're saying this whole thing needs to equal 0. For this equation to be true, we need c equal to pi over 2. So what we can do is we'll just plug that right back in here. And we can write our equation, pi over 2 minus arctan s over a. And this is going to be our f of s function. And then with this right here, we can get back to our original problem, get back to our fs. We need to evaluate this here at 0. So let's see what that's going to be for f of 0. That's going to give us our value for this integral right here at 0. So we're going to have pi over 2 minus, you plug here arctan of 0, but arctan is 0. That's just 0. So our f of 0 value is going to be just pi over 2. And so the crazy thing about this is just a constant value. It has no dependency on this a value. This a value doesn't matter, so pi doesn't matter, and e doesn't matter. And the problem I did before, we did just sine of x, so it was 1, but it doesn't matter whatever a value you use. Our original problem, we have this set up as just f of 0 minus f of 0. So this is just going to become pi over 2 minus pi over 2. And so for our solution of this, we just get 0. So like I was saying at the beginning of the video, you might have been able to just do this, looking at the thumbnail, just doing this in like 3 seconds. The key is not even recognizing that it's pi over 2 for this f of 0 function, but just recognizing that it's a constant value, that there's no dependency on the a value. Because once you know that this integral is the same as this integral, of course, when you subtract them, they need to be 0. So there is a really quick way to do this, but it's kind of interesting to see how it all works and how this is so different than the cosine case, which doesn't really work this way at all. Okay, so there you go. Strange case where you're going to get kind of the same value no matter how you do this one, no matter what constants are on the x. Thanks everyone for watching. Have a good day.